back when you did redox equations in Chem 1, you balanced them. You, if you remember, identified what was oxidized, what was reduced. You connected the species that were oxidized by little lines, and you said how many electrons there were. And then you connected the species that were reduced by lines and said how many electrons there were. And then you multiplied as appropriately each type of species so that the number of electrons balanced out. Now that's effectively how we're always going to balance redox equations, because when you balance a redox equation, you not only have to balance everything else, the atoms, but you also have to make sure that the number of electrons being transferred is also balanced. However, when we're dealing with these net ionic versions of the redox equations, a lot of times it's more useful, more convenient, rather than to do what we did last time with the entire equation, but to break it down into the half equations. And we're going to be using the half equations extensively as we go through this chapter to help us study the redox process, to break down that big redox into the reduction and the oxidation. So it's a worthwhile exercise to get used to the half equations, to use those now to balance these redox equations, particularly the ones where the net ionic nature of the equations and the fact you have to add in H plus, OH minus and water or whatever can complicate the issue. And of course it also gives a great way to come up with a couple of questions to throw on the exam for you. So anyway, let's learn how to do this, but in a very simplistic way. First of all, using an equation that there is absolutely no reason why you couldn't just balance it anyway. But let's take Na solid plus Cl2 goes to Na plus Cl minus, and let's break it down into its half equations. To do this, you have to, of course, be aware and able to assign oxidation numbers. Sodium is 0, sodium plus is 1 plus, 0 to 1 plus. You lose an electron, it's oxidized. There we are, it's the oxidation half equation. Cl2, chlorine is 0, Cl minus, chlorine is -1, and so the reduction is the 0 to the -1, Cl2 to Cl minus. One of the things you have to do immediately to you start trying to talk about a half equation is you have to identify the important atoms. In this case, that's the chlorine, not much else choice, and make sure that that number of atoms is balanced. Doesn't matter about anything else right now, but if you haven't balanced the important atoms right at the start of the process, you're going wrong. Something is bad. So we have 2 chlorines on the left, we need 2 chlorines on the right. Now let's study this process in terms of the reduction. Well, we've got reduction is gaining electrons. In this case, each chlorine is going from 0 to -1. It gains 1 electron, but we have 2 chlorines, that's why you had to balance it. So therefore, in order to make this half equation describe the reduction properly, we're going to have to put in the 2 electrons as reactant. Cl2 plus 2 electrons goes to 2 Cl minus. Same type of process up here with the oxidation, but it's much easier. Oxidation is the loss of an electron. Loss of electrons, in this case 1 electron. Sodium goes from 0 to 1 plus, therefore Gaia loses that electron. Now notice these 2 half equations. Each one describes the process it's supposed to describe. The reduction one describes the 2 electron reduction of Cl2. The oxidation describes the 1 electron oxidation of sodium. When we're going to put these together in the whole equation, remember the electrons must balance out. And so we have to combine these equations by multiplying us appropriately in order to do that. So we've got 2 electrons here, we got 1 electron here. How do you make 1 and 2 equivalent? Well, that's easy. You multiply the oxidation one by 2, because the oxidation needs 1 electron, produces 1 electron. You have to have 2 oxidations to match up the reduction. So when we do that and add them together, we get what you could have done anyway. 2Na plus Cl2 goes to 2Na plus Cl minus. Anyway, that's the process. Now let's put everything together in a really interesting way. Permanganate plus chloride goes to Mn2 plus Cl2, and we're going to be doing this in acidic solution. You could have probably told that already, because in acidic solution permanganate goes to Mn2 plus. So we've looked at both of these half equations before. That is intentional. Let us assign oxidation numbers though. So the manganese there is +7, the Cl is -1, the manganese is +2, and the Cl2 is 0. Switch those around, never mind. Break out the half equations, reduction and oxidation. The reduction 1, manganese goes from 7 to 2, it's reduced. Oxidation, chloride goes to chlorine, -1 to 0. First thing to always do, balance the important atoms. Well, in this one, I've got 1 manganese, that's great. Reduction is where something gains electrons. It's going to gain 5 electrons per manganese. We have 1 manganese, so therefore we need to put 5 electrons in to the manganese half equation. And now we have described the reduction process. Notice we haven't balanced the oxygens, we haven't balanced the charge. We don't care about that yet. What's important is we got the manganeses balanced and we've got the correct description of the reduction. Now let's go to the oxidation. Well, again, got to balance the important atoms, 2 chlorides on the left to balance out the 2 chlorines on the right. Oxidation is losing electrons, 1 electron per chlorine. We've got 2 chlorines, therefore we need to have 2 electrons being produced by this oxidation. Now, at this stage, we could go ahead and complete the half equations by including the H pluses and the waters like we did on the previous show. But the trouble is that while this would be fine in this, if both half equations are ones in which you need to balance it out using extra H's, extra O's and so forth, then it gets really complicated. What I like to do is once I've got what I call the balanced redox part, okay, this describes the reduction, this describes the oxidation. What I like to do is bring them together now so that I am considering further balancing on the whole equation rather than 2 halves. A lot of times it just halves your work, quite frankly. So I've got 5 electrons in the reduction, I've got 2 electrons in the oxidation. I need to multiply these appropriately so I get the same number of electrons. And sometimes it's as easy as cross multiplying, sometimes you need to be a bit more sophisticated. This one, how do I get 5 and 2 equal? Well, I multiply 5 by 2 and I multiply 2 by 5. And when I do that, I will have 10 electrons involved in this whole process. Remember that number 10 for later, how we got it. The number of electrons involved in the balanced redox equation is a very important number we'll address in a little while. So anyway, here's where we got it. Twice the reduction, 2 manganese, 2 pluses, 5 of the oxidations, 5 Cl2, and of course 10 Cl minus. Now we'll go through a little process that we applied a couple of times in the previous show. We need to balance the charge. Well, on the left hand side we have 12 minus, on the right hand side we have 4 plus. Make sure you see that. Now count to 3. I'm going to count to 3 and then I want you to yell out at the computer screen how out of balance the charge is. 1, 2, 3. And I bet some of you yelled 8. It's 16 out of balance. It's not between 12 and 4, it's between -12 and 4. 16 out of whack. Now, we are in acidic solution. If we're in acidic solution, what do we use to balance the equation? H plus. And what side should we put it on? The side that needs to become more positive, which is, of course, the left-hand side. Okay? So there we are. We've now included our H plus. The charge is balanced. And you could always check. We got 16 plus minus 2 is 14, minus 10 is 4. On this side, 2 times plus 2 is 4. Next step, look at the oxygen atoms. 4 on the left, 8 on the left, none on the right. So how out of whack are they? They're 8 out of whack. What do we use to balance oxygens? We use water. And what side should we put them on? The side that needs them. So that is, in this case, of course, going to be the right. So there we are. Hopefully we have balanced everything we need to do. We've got the H's, the O's balanced, the manganese is balanced, the charge balanced, and the electrons all cancel out nice and balanced. We can check ourselves with the hydrogens, 16 on the left and 16 on the right. Once we stick the half equations together to get the whole equations, we can do the same thing with the potential. We can start talking about, well, if the potential of this reduction is this and the potential of the oxidation is this, what's the potential for the whole reaction? And so, for example, if we look at this one, from our list of potentials in the previous slide. Cl2 plus 2 electrons goes to 2Cl minus. Sodium goes to Na plus an electron. Reduction potential 1.36. Oxidation potential 2.71. Okay? Why don't you now say, well, if that's the reduction potential and this is the oxidation potential, what's the overall potential for the reaction? And the answer is just add them together, 4.37 volts. Okay? There is no need to worry about balancing, because what this refers to, what the potential refers to, is the cliff height. So we got one sodium going off the cliff. The cliff is 2.71 volts high. Yeah, we need, when we balance the whole thing, 2 sodiums to produce the 2 electrons that we need for the reduction, but that just means it's 2 sodiums jumping off the same cliff height. Okay, if you have 2 men on top of a cliff, the cliff doesn't suddenly become twice as high. Okay, so you don't have to worry about the electrons. The reduction potential for chlorine is always plus 1.36 volts. The reduction or the oxidation potential for sodium is always plus 2.71 volts. So the total potential for the reaction, 4.37 volts. We usually don't call it a reaction potential. We usually call it a cell potential. And we'll see the reasons for that in a little while. Let's do the other one that we just balanced. Look it up in our little book, and we want the reduction potential for manganate. Permanganate plus 5 electrons goes to Mn2+. We want the oxidation potential for chloride. Well, the oxidation potential for chloride is easy. It's just negative 1.36 volts. However, when you look up, even though this was the half equation that we used to balance the equation, when you look up tables of half equations, you'll see the full half equation. So we would not look up just manganese plus 5 electrons goes to Mn2+. We would look up, of course, the manganese permanganate plus 8H plus 5 electrons goes to Mn2+ plus 4H2O, and the reduction potential for that is plus 1.51 volts. What is E cell for this one? Plus 0.15.